Hi, I'm Henry Segerman. In this video I'm going to show you some of the math behind the 15 puzzle, and I'm also going to show you some variants of this puzzle which shake up that math and change how it works. Okay, so here's the 15 puzzle. You have these tiles in this frame that you can move around in some pattern, and you can scramble up the puzzle and then you have to try and get them back to the original order. A natural question is whether or not you can get to every possible rearrangement of the tiles. The puzzle inventor Sam Lloyd once offered $1,000 if you could get from the starting position to this position where 14 and 15 are swapped. This was a large amount of money at the time, but the money was safe as it had been proved impossible to do 10 years earlier by Johnston and Story in 1879. So why is it impossible? First of all, let's say that there are actually 16 tiles, where one of the tiles happens to be the empty tile. Now, if we were allowed to just pick up tiles and swap any pair, then you can get to any pattern of tiles you want. For example, I could get to the 15-14 state by just swapping the 14 and 15 tiles. In the real puzzle though, at each step you're only allowed to swap the empty tile with one of its neighbors. Here's the key idea. Suppose you make a bunch of these empty swaps and get the empty tile back to the bottom right hand corner. How many swaps did you do? You might just do it in 2. 1, 2, the empty tile is back in the bottom right corner. Or I could do it in 4, 1, 2, 3, 4, or 6 or 8, but notice it has to be an even number of swaps. The reason for this is that each swap that takes you to the left must be matched with some swap that takes you back to the right. And the same thing with anything that moves you up has to be matched with something that moves you down. So in order to get back to the bottom right corner, you must have done the same number left as you did right, the same number up as you did down, so it has to be an even number. It turns out that any pattern you get by doing an even number of swaps can only be done with an even number of swaps, and any pattern that can be made with an odd number of swaps can only be made with an odd number of swaps. This parity principle is a bit beyond this video, but if you believe it, then you now know that the 15-14 state is impossible to get to by sliding the tiles, and this is because it can be done with one swap and one is odd. Okay, so what would happen if we somehow added an extra way to slide a tile that changed the way this parity argument works? For example, maybe I could connect this bottom right tile directly to the top left tile, and maybe that would change something. Well, here it is. This is the 15 puzzle wrapped around a torus with the top left tile here right next to the bottom right tile here. And if you count over here, what that means in terms of the parity argument is that one could go from the empty tile via a path of length 1, 2, 3, 4, 5, 6, and then the extra move to move this tile here over to here, and that would be a length 7 path, which is odd. So let me do that over here. So just to start off with, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is the starting position, and let me do that length 7 path. 1, 2, 3, 4, 5, 6, 7. So the empty tile is back in the lower right hand corner. And then we never use that move again. And then what we're going to be able to do is get to that pattern where 14 and 15 are swapped. And I'm not very good at this, so I'm going to speed up the video. Alright, and I think I'm good. So on the top row, 1, 2, 3, 4. Next row, 5, 6, 7, 8. 9, 10, 11, 12. And 13, 15, 14. So just adding that extra connection between the top left and the bottom right is all you need to be able to solve the impossible puzzle. Here's one further addition to the story, a different way to change the 15 puzzle to get an odd length loop. This is the 15 plus 4 puzzle, where I've jammed an extra 4 tiles into the puzzle on another 2x2 part of the frame. And the frame hinges to allow you to slide tiles across the hinge when it's flat. Of course, when it's hinged in different ways, then you can't slide them across. So this has a length 5 path. If you go around the center, then 1, 2, 3, 4, 5. That's odd, of course. So maybe that changes the answer. Just to throw another spanner in the works, notice that I have dots underneath the 9, the 6, and the 8. And those are to record the orientation. So why do we need to care about that? Well, as you go around the central vertex, you're going to end up rotated. So to see that, the 11 is the same way up as the 10, which is the same way up as the 6, which is the same way up as the 7, which is the same way up as the 16. But the 11 is not the same way up as the 16. It gets rotated by 90 degrees when you go around that central vertex. So maybe now you need to care about the orientation. You need to know that the 9 is not the same as the 6, and you need to know which way up the 8 is. So maybe that changes the answer. Can you get to every pattern of the tiles, including both their positions and their orientations? All right, well, I'll leave you with that. Thanks for watching.